Hello everyone, my name is Quy Pham, and I'm currently a fourth-year PhD student in the Department of Mathematics at the University of Rochester. My advisor are Professor Iosevich and Professor Allan Greenleaf. My research interests lie between the intersection of harmonic analysis and geometric measure theory. Today, I will talk about my work on the distance set problem and Falconer type functions using different approach, projection theory, and Fourier integral operator. Here is the outline for my talk. First, we will begin with a brief review of the distance set problem. Then I will present my result regarding the distance set problem for Cartesian products. And the proof of the result will rely on projection theorems. Finally, on the last session, I will discuss general configuration problems using Fourier integral operators. Let's begin with the distance set problems. So this is one of the central problems in geometric measure theory and fractal geometry, which has deep connection with harmonic analysis. Before we state the problem, I need to briefly recall the definition of Helmholtz dimension. So for a set A in the Euclidean space Rd, we define the dimension using Helmholtz measures Hs, and this definition involves covering the set A by small sets with diameters smaller than deltas, summing all diameters raised to the power of s, and take infimum over the sum. So the Helmholtz measures of this set is the limits of the quantity when delta approaches zero. The Helmholtz dimension of the set A is then the critical number where the Helmholtz measure jump from infinity to zero. These Helmholtz dimensions give us a way to measure the size of fractal sets. Now we will introduce distance set problem. Given a set E in a Euclidean space, we denote delta E as the set of all pairwise distance in E. The central question is the following. How large does Helmholtz dimension of a compact set E need to be to guarantee that the distance set formed by E has positive Lebesgue measure? Falconer proved that if the Helmholtz dimension is greater than d plus 1 over 2, then we have the positive result. And he conjectured that the exponent d over 2 is the right threshold for this problem. The following tables give us the improvement for the Falconer distance conjectures over 4 decades. So the best known threshold for the case D with 2 due to Good Iosevich, Owen Wang in 2019, and for the case dimension greater than or equal to 3 due to Yu, O, Ray, and Yang. A natural variation of this problem is to look at sets with a specific structure. And one of the common structure in analysis is the Cartesian product. So in this context of Cartesian products using Fourier analysis and additive combinatorics, Iosevich and Liu in 2016 proved the following result. They proved that if the set E has product structure, then we can ensure that the distance set has positive Lebesgue measure if the dimension of the set E larger than d squared over 2d minus 1. And we note that this exponent is larger than d half, but smaller than d half plus 1/3. So there is a significant room for improvement if we want to get closer to the exponent d half. This brings us to the first result. So in this result, well, we need to recall the Fourier transform of a measure by this quantitative, and the Fourier dimensions of a set A given by this. Basically, the Fourier dimension measure the decay rates of the Fourier transform of the measure supported on the set A. So our first result for the distance set problem is the following. Assume that A is a compact set had a form A1 cross A2, where A1 belong to Rm and A2 belong to R to the T minus M. Assume that we have the relation between Hausdorff dimension of A1, Hausdorff dimension of A2, and Fourier dimension of A2 like this. Then we ensure that the distance set has positive playback measure. And in particular, if the set A2 is a Salem set, meaning that the Hausdorff dimension and the Fourier dimension equal to each other, then this condition tells us that if the dimensions of the set A exceed d over 2, then we have positive result. And to prove the theorem, we also prove a variant of the distance set problem for the distance set between two sets, where one of them lies in a hyperplane. So if the sum of the dimensions larger than d, then we ensure that the distance set between the two sets has positive Lebesgue measure. The key insight of our proofs is the connection with the projection theory in geometric measure theory. And heuristically, we will want to calculate the distance from a set to a point in the hyperplane, and this geometrically equivalent to projecting another set onto the lines. So now I will introduce projection theory. So projection theory studies how fractal sets behave under orthogonal projections onto lower dimensional subspace. And the core question is how large is the dimension of the projections for most directions or most lower dimensional subspace. So specifically, we look at the projection onto lines. For any direction E on the circle, we define the orthogonal projection onto the line generated by direction E that go to the origin. This map is elliptic, so the dimension of the projection can never exceed the dimension of the original set. But for random or typical directions, the equality should hold, meaning that the projections should have large dimensions as possible. And this intuition was formalized by Max in 1994. He proved that if the set in the plane had dimensions smaller than 1, then the dimension of the projections is as large as possible for almost all direction. And if the set E has dimension larger than 1, then the projections has positive Lebesgue measure for almost all directions. Also, we would like to consider the bad direction where the projection is small, and the directions are called exceptional set. These sets are indeed very small, and we would like to know how small the dimension of these sets. So Kaufman, Matila, and later by Falconer, they gave estimate for the dimensions of the bad directions. For our purpose, We only look at part B. So if the set is large enough, then the set of directions such as the Lebesgue measure of the projections equal to zero, then the set of bad directions have small dimensions depend on the dimension of the original set. So now we can prove our result. So recall that in theorem 4, we assume that we have compact sets E and F is contained in a hyperplane with the sum of dimensions larger than D, and we would like to prove that the distance set have positive Lebesgue measure. So first, we note that since the distance function is invariant under rotation and translation, we can assume that our set F is actually lie in the hyperplane with the last coordinate equal to 0. Also, we note that if the set E is contained in the same hyperplane, then the result follow from Falconer theorem would say that the distance set between E and F has a positive Lebesgue measure. So now by picture and holding, we can assume that the set E is actually concentrated in a set or an open set U that's away from the plane. Here the last coordinate is larger than C. So by restricting the set E to an open set U away from the plane, we can perform the following trick. This is the main trick for the proof of theorem 4, that for a fixed y in the plane and fixed x in the set E, we can write out this square distance between x and y formula, and we rearrange it to the form of dot product plus a constant that depends on y, and we define this function as phi of x and y prime. We observe that when we write this square distance at the union of we can we can write the phi conversion that pin at the point y at delta phi of y e, and we observe that the square distance between the set E and F is actually the union of all phi configuration that pin at y of the set E. And we only need to show that there exists some y for the right-hand side of this equality have positive Lebesgue measure. This will immediately imply that the distance set between E and F has positive Lebesgue measure. The crucial observation here is that for fixed y, the map phi of y is essentially a projection map. In this, if we denote this map by theta that transform x prime and xd to x prime, the length of x prime square plus the length of xd square, then we can write the image of E via the map C via the projections of E prime. So this can be summarized via the following diagram. Assume that we have the set E and the set F on the hyperplane. So all the distance from a point in the hyperplane to the set E can be transformed to the projections of the set E prime to the line generated by the direction E tilde. So because this map transform E to E prime, this map is bielliptic onto image, we have that the dimension of E prime E actually equal to the dimension of E. Now we can apply theorem B by Falconer that tell we that the dimension of E prime and F prime here have the sum larger than D, then there exists some direction that the projection has large dimensions, or in this case has positive Lebesgue measure. This implies that our distance sets from E to F have positive Lebesgue measure. And this finishes the proof of theorem 4. Now we can return to the Cartesian product setting. So indeed, theorem 3 follows from theorem 4, because if we have a Cartesian product A equal to A1 cross A2 with satisfying this condition, then we can write out the distance functions x to y as functions, the distance between the point x prime xd minus yd to y prime 0. This is indeed the distance between a point in E to the point in F, where E is A1 cross with the different set of A2, and F is A1 cross with 0, where F, we can see now that's E contained in the hyperplane. So this is very important for us. That we can apply theorem 4. We have the following claim that if we know the information about the Helmholtz dimension and Fourier dimension of the set A2, and the sum of them is larger than S, then we can conclude that the dimensions of the different sets of A2 is greater than S. By assumption, we have that the following relations for dimension of A1 and A2. If we use the bold claim, we see that we can replace this by the Helmholtz dimension of the different sets. And the Helmholtz dimension of A1 with the Helmholtz dimension of the different set give us the Helmholtz dimension of the set E. So we have the dimension of E and F have the sum larger than D, which satisfy the condition of theorem 4 for the distance set between a set in a plane with a general set. Therefore, we can conclude that the distance sets between E and F had positive Lebesgue measure, which implies that the distance set of our product set has positive measure. So we only need to prove the claim above. So the proof of the claim is basically very standard in geometric measure theory, and we need to use Forstmann-Lemma. Basically, this Forstmann-Lemma give us the equivalent definition for Helmholtz dimensions. We define the energy integral of the measure mu as the double integral with the kernel x minus y to the negative s. And using Fourier transform, we can rewrite this as the integral of Fourier transform of mu squared times c to the s minus d. And we know that from Forstmann-Lemma that if a measure mu satisfies Forstmann condition, then the energy integral is finite for all t smaller than s, And in particular, we have this definition. Basically, if we have the half dimension larger than some constant s, then the energy integral, uh, n-dimensional energy integral is finite. Now here is the calculation for the lemma. So we recall the lemma that we assume that the sum of half dimension and Fourier dimension of set E2 is greater than S, and we want to conclude that the half dimension of the different sets is larger than S. So by Forstmann lemma and by the definition of Fourier dimensions, we can choose a measure mu supported on E2 so that the energy integral is finite. Also, we can take a measure V on the negative A2 so that this Fourier transform has decay ray beta over 2. So we note that the convolution measure mu convolved with V is supported on the different sets. So by studying the energy integral of that convolution measure, we can apply the assumption on the energy integral of measure mu and the decay rate of Fourier transform of V. So this will give us a constant, and the energy integral of the measure mu is finite. This implies that the energy integral of convolution measure is finite. And we can conclude that the half dimension of the different sets is larger than the required dimension S. So this finishes the proof of our result. So now in the final part of the talk, we want to discuss my results on configuration problems using Fourier integral operator approach. And the general question is the following. Given k set ei, a function phi, how large the sets need to be to ensure that the configuration set has positive playback measures? For example, we might look at the congruent triangles by mapping triplets of point x, y, and z to their distance x minus y, y minus z, and x minus z. So there are a vast literature on the configuration problem from covering from chain, triangles, simulates, dot products, area, and volume for sets on Euclidean space or set on spheres, on cone, paraboloid, or Riemannian manifolds. In a series of 3 papers, Greenleaf, Iosevich, and Taylor developed a framework using Fourier integral operator technique to study Matillas-Strolling type configuration problem, giving global bounds on the dimension of set EI, ensuring that various configuration sets had non-empty interior, which is stronger than having a positive playback measure. As an application, they gave a short proof for the following result by Parsons and Romero Ascosa in 2023 that let E be a compact set in a Euclidean space with dimension greater than 4, and dimension of E satisfied that it exceeds 2D plus 3 over 3, then the set of congruent class of triangles with vertices in E has non-empty interior. Now I want to sketch the framework developed by Greenleaf, Iosevich, and Taylor that they will let mu I at the Fortman measure supported on its set EI, and then they define a natural measure on the configuration set by the following relation. In other words, V is just the first forward measure of mu1 cross to mu k via the map phi. And the approach that they introduced was to prove that the natural measure V is actually absolutely continuous with respect to Lebesgue measure, and its density is continuous function of the configuration parameter. This will imply that the set, um, the configuration set, has non-empty interior. To prove that, they associate the configuration functions with the families of generalized random transform. This generalized random transform take integrate functions over the level surface of the configuration map phi, where x and y here are partition of the variables. So the problems become proving L2's overlap estimate for the operators, where the L2, we recall the definition of the L2 base overlap space with fractional order S are the following. By studying L2's overlap estimate for the generalized transforms of this form, Greenleaf, Iosevich, and Taylor show that uh, if the operators have nice mapping properties, then the measures V is well behaved. And in this continuous, and this will imply that the configuration set has non-empty interior. So I want to adapt this framework to study the Falconer type problems. So because in their approach, uh, the math is so in some case that uh, their approach cannot provide um, sharp bounds or even like vectors that we cannot find satisfy the condition. So by adapting this method to study the L2 norm of the natural measure V instead of the L infinity norm, we often the Falconer type result for a broad class of smooth functions, and this will work even in the case that uh, the L infinity norm does not give a positive result. So for simplicity, we will state that result for a smooth function in three variable. So let's assume that f is a smooth function on an open set omega, and assume that locally our function f depend on own variable x1, x2, and x3, and it does not have the form uh, g of h x1 plus k x2 plus l x3. Then we assume that A, B, and C are compact sets such that uh, the the product of A and B and C is in the omega. Then we denote delta F as the image of A cross B cross C via F. We have the following conclusion that if the dimensions of A, B, C have the sum larger than 2, then we have the positive Lebesgue measure. And we also have similar result when the dimensions, the sum of dimension of ABC smaller than 2. So I want to emphasize that theorem 7 is sharp, and it recovers the result on quadratic polynomials in three variables by Pham and Centin. This theorem is sharp. For example, we can take a f as x times y plus c, and we take a equal to 0, b and c equal to the unit interval. Then we can see that the dimensions of A plus dimension of B and dimension of C equal to 2. But the image set is actually just 0. Therefore, it has 0 Lebesgue measure. Furthermore, the condition that f must depend on all variables and do not have to form the sum of separable functions like g of x plus ky plus lz. This condition is necessary. Indeed, if the function have depend on two variables, then we may not have positive result. And if f have the form of x plus y plus z, then we can find compact set A, B, C in the unit intervals such that the sum of z dimensions, they nearly is equal to 3, but the image sets have 0 Lebesgue measure. So as an application, we study the distance problem for a general set with a set lying a smooth curve. We say that gamma from 0, 1 to R2 is a regular smooth curve if gamma is smooth and it satisfies the derivative is not equal to 0 for all t. Direct calculations show that the functions the distance functions between a point xy to a point on the curve given by z satisfy the hypothesis of our theorem for some open set away from the curve. Therefore, we obtained the following result. So if A and B are compact set, where A is a general set and B is set it contained on the curve, and the sum of them the dimensions exceed 2, then we have the distance set between A and B have positive Lebesgue measure. Next, I will sketch the proof of our theorem 7. Assume that we have a map F that satisfies the hypothesis of theorem 7, and we have three compact sets A, B, C. By Forstmann lemma, we can take the measure mu I on A, B, C for I equal to mu1, mu2, and mu3. And we let V be the natural measure on the configuration set, or in other words, that's a put forward of mu1 cross mu2 cross mu3 via F. We will show that the L2 norm of the measure V is finite, and this will indeed imply that V is absolutely continuous with respect to Lebesgue measure, and we can conclude that the configuration set has positive Lebesgue measure. To show that the L2 norm is finite by Plancherel, we can write this at the integral of the Fourier transform square. And then we can write it out as an integral oscillatority integral with phase functions defined by our map F. We then can partition this integral like the following. So we can partition our variable x and y into two blocks with mixed variable from x and y. For example, here we have x1, x2, and y3. Similarly, we have y1, y2, and x3. Then we define the corresponding operators denoted by R. Then we can represent our energy integral as this pair of the operators action on mu1 cross mu2 cross mu3 and with the mu1 cross mu2 and mu3. So this will reduce our problem to bounding the operators R. Observe that our operator R is indeed a Fourier integral operator associated with a canonical relation that is actually conormal bundles of the level set where fx equal to fy. Direct calculations give the order of this operator in -1. And by standard estimate for FIOs, we have that these operators map function in hs to s plus 1 for all s in R. If certain condition holds, and in our setting, this condition is actually the Mexican Hessian matrix has determinant different from 0. So if the determinant is non-zero, then the operator maps between the correct solar lab space and the energy integral converges. Therefore, we can prove the theorem. So what if the determinant is 0? The determinant entry star here is 0. Then we know that we can calculate the determinant of that matrix, and this gives us if the determinant is 0, then the estimate for Sobolev estimate for our operator does not hold. So we perform calculation for all possible operators corresponding to all partition of variable x and y, namely we we have like R12, R13, and R21 here. Then we obtain the following system of PDEs. And using the conditions in our theorem, we can solve this system of PDEs and this will tell us the function that failed the test. And the claim is the following. The solutions of this system of PDE are precisely the function that have this form. And this finishes the proof of the theorem. So thank you for listening to my talk.